Hi everyone, today we are going to study adjacency matrix. Now as an alternative to the incidence matrix, it is sometimes more convenient to represent the graph by its adjacency matrix or the connection matrix. So the other name for an adjacency matrix is a connection matrix, and it is used as an alternative to the incidence matrix. The adjacency matrix of a graph G with n vertices and no parallel edges is an n by n symmetric binary matrix. That means if you talk of an adjacency matrix of a graph which contains n vertices, first of all, the first condition is that there shouldn't be any parallel edges in the graph, because the adjacency matrix is not capable of representing the parallel edges. Then it is an n by n symmetric binary matrix. That means the same number of rows and the same number of columns. The matrix will have the same number of rows and the same number of columns. So if I represent the adjacency matrix by x, then x equals to xij, where xij is representing an element at a particular coordinate position for the ith row and jth column, such that if xij equals to 1, that means the value at this particular coordinate position for the ith row and jth column would be 1 if there is an edge between the ith and jth vertices. So here we are taking vertices into account. If you remember, in case of incidence matrix, we were considering the vertices by edges. So the rows were represented, your vertices and the columns represented your edges. But here we are showing the incidence with the help of vertices themselves, and edges are not included here. So that is why it is an n by n matrix, that is vertex by vertex. So that is why it is a symmetric binary matrix. So same number of rows and same number of columns. Why? Because we are considering vertices for the rows also, and we are considering vertices for the columns also. So the value at the coordinate point, the value at a particular coordinate point for the ith row and the jth column would be 1 if there exists an edge between the ith and jth vertices, and it would be 0 if there is no edge between the ith and jth vertices. So the condition is that there should be an edge between the ith and jth vertices. If there is an edge, the value at that particular coordinate point would be 1, or else the value would be 0. Now we'll consider through an example graph. So if this is a connected graph and we have to draw an adjacency matrix for this connected graph, since I said it is an n by n matrix, that means same number of rows and same number of columns, and n here is representing the vertices of the graph. So if I look at this graph, I clearly can see there are 6 vertices in this graph. So that means it will be a 6 by 6 matrix, right? Because there are 6 vertices, and these vertices are used for the rows also, and these vertices are used for the column also. So obviously same number. It is a symmetric binary matrix. Now the value at a particular coordinate point for the ith row and the jth column. This is the ith row and this is the jth column. Now this I and j could represent anything. It could be the first row, it could be the second row, third row, and so on. So in general, for the ith row and for the jth column, the value at a particular coordinate point would either be 0 or it would be 1. It is 0 if there is an edge between the ith vertex at the ith row and the jth column, and it would be 0 if there is no vertex, if there is no edge between the vertex at the ith row and jth column, and it would be 1 if there is an edge between the vertex at the ith row and the jth column. So let's see. Now vertex v1, of course there would not be any edge from vertex v1 to v1 itself. Unless it is a self loop, there wouldn't be any edge from the vertex to itself. So that means for v1 to v1 there is no edge, so we will have the value 0. Now next, moving on, v1 and v2. Is there an edge from vertex v1 to vertex v2? Yes, there is an edge from vertex v1 to v2. So we will have a value 1 here. Then is there an edge from vertex v1 to vertex v3? V1, there is no direct edge between vertex v1 and v3. So obviously it will be a 0 here. Then from vertex v1 to vertex v4, v1 is here and v4 is here. There is no direct edge between v1 and v4, so there will be a 0 over here. Then if we look at vertex v1 and v5, so there is clearly an edge between vertex v1 and v5, which is edge e2. So that means there exists an edge, hence this coordinate point will have the value 1. Then between vertex v1 and v6, so there is an edge between vertex v1 and v6, which is e6. So that is why at this particular coordinate point for the vertex v1 and vertex v6, we will have value 1. So this way you can make the complete adjacency matrix, and here we are not taking the edges into account, here we take the vertices into account, and then we find the incidence between the vertices and the edges. But here the rows are also represented using vertices and columns are also represented using vertices, so it is an n by n matrix. So that is why we say that the incidence, the adjacency matrix is an alternate to the incidence matrix. The only difference is that in case of incidence matrix, you are representing, you are using both your vertices and edges, wherein the vertices are represented as rows and the edges are represented as columns. And here you are taking vertices only both as rows and columns. But the purpose is same in both the cases. What are we trying to represent? We are trying to represent the incidence between the vertices and the edges. That their incidence is, in case of incidence matrix, incidence is represented using edges and vertices, and in case of your adjacency matrix, the incidence is represented using the vertices only. So hence you can clearly see how we can make an adjacency matrix for a connected graph. So anywhere if there is between an edge between those two vertices, it will be a 0, and anywhere if there is no edge between two vertices, it will be a 0, and anywhere if there is an edge between the two vertices, there will be a 1. Like there is no vertex from v1 to there is no edge from v1 to v1, so a 0 here, but there is an edge from v1 to v2, so a 1 here. So anywhere you find an edge between any two vertices for the ith row and jth column, you place a 1 there, and anywhere where you don't find an edge between the vertices at the ith row and jth column, you place a 0 here. So this is how you can draw the adjacency matrix for any connected graph. Now this is a simple graph and its adjacency matrix. Now there are certain observations again in case of the adjacency matrix that can be made. First of all, entries along the principal diagonal of the adjacency matrix are all zeros if and if only if the graph has no self loops, right? So this graph clearly has no self loops. So in that case, you will find out that the principal diagonal, this is the principal diagonal of the adjacency matrix. This is the principal diagonal, and this principal diagonal of the adjacency matrix will always be 0 if there is no self loop, because since there is no self loop, that is why there is not an edge from the vertex to itself, right? And all the diagonals represent the same vertex. v1, v1, v2, v2, v3, v3. So the principal diagonal will be 0 if there is no self loop in the graph. A self loop at the ith vertex corresponds to xii equals to 1. So basically, if there is a self loop at any of the vertex, so that would be represented as xii equals to 1, because it is for the same vertices. Self loop is when there is a edge from vertex to itself. That means vertex is same in both the cases. Even in the row the vertex is I, and in the column also the vertex is I, and for that coordinate position the value will be 1. Like here, for the row also the vertex is v1, and for the column also the vertex is v1. But since here we do not have a self loop, so the value at the coordinate position would be 0. Again here the row is also v2 and the column is also v2, so a 0. Row is also v3, column is also v3. So this is how you represent the self loop at the ith vertex. The definition of adjacency matrix makes no provision for parallel edges. This is the very first thing that I told you when I was giving the introduction for adjacency matrix, that it does not make any provision for the parallel edges, or in other words, you cannot represent parallel edges using adjacency matrix. That is why the adjacency matrix was defined for graphs without parallel edges. So one restriction of the adjacency matrix is that you can represent a connected graph using adjacency matrix if and only if it does not have any parallel edges, but self loops can be included.